Hello and welcome. My name is Franz Polster. This is the second of two videos on numerical methods for the calculation of exponential approximations. It is a follow-up to my video on the theory of exponential approximation. Familiarity with that video is assumed. In particular, the terminology introduced there, as well as the statements, corollaries, etc. of the theory, will be used without further explanation. Iterative algorithms will be presented which calculate best approximations with respect to v sub n0 for continuous functions. This is the algorithm and method of Braess, an algorithm which for the purpose of this presentation is referred to as Newton-X, since the core of it is the application of the Newton algorithm for finding the zeros of vector-valued functions. And finally, FJP-X, an algorithm which calculates best approximations with respect to v sub 10 only. These algorithms deal with simple exponential sums only. In the theory video, it has been pointed out that the parameter a can be considered a vector with two n components, which are the coefficients ai, ti of the respective exponential sum. This is exactly what these algorithms do. They operate on simple exponential sums in terms of their vectors ai, ti. Direct non-iterative algorithms are the subject of the video Direct Methods. Let us start now with the algorithm and method of Braess. Given an exponential sum e of a0 of v sub n0, which is not already a best approximation, the algorithm of Braess computes a sequence of better approximations in v sub n0. If there exists a best approximation, this sequence should finally lead to that best approximation. In order to compute a best approximation with respect to v sub n for a given n greater than 1, Braess proposes to calculate successively the best approximations with respect to v sub 10 and then v sub 20 and so on until you finally reach set v sub n0. Braess called this an inductive process, which works like this. Start at v sub 10. The algorithm of Braess computes a sequence of better approximations and ends with the best approximation with respect to v sub 10. This best approximation is the starting value in v sub 20. The Braess algorithm computes a sequence of better approximations in v sub 20 and ends with the best approximation. Continue on following the scheme until we reach v sub n0. We will return to this process and elaborate on the starting functions after the presentation of the algorithm of Braess, which is next. For this purpose, we need the following terminology and notations. This is the gradient of exponential sum e of a. It consists of the partial derivatives of e of a with respect to all coefficients ai and ti. Wn denotes the linear space generated by the components of the gradient of e of an, and dn is the dimension of this linear space. As you will see, the algorithm of Braess makes use of the fact that the best approximations with respect to linear space Wn exist and are unique. And finally, capital Fn denotes the error function f minus e of an. With these definitions, this is how the algorithm of Braess calculates sequences of better approximations. Let the exponential sum e of an be the nth element of the sequence of better approximations calculated so far, which is not yet a best approximation. Step 1 finds the best approximation En for the error function capital Fn with respect to the gradient space Wn of this exponential sum. That is, find a vector Rn with dn components such that this function En of x is the best approximation with respect to gradient space Wn. Since, as has been noted above, Wn is a linear space, the best approximation En exists. With that function En, in step 2, calculate epsilon n, which is called by Braess the improvement. In step 3, by successively dividing by 2, a constant Cn greater than 0 is determined such that this inequality holds. That is, the norm of this error function is less than that of capital Fn. Thus, this exponential sum is a better approximation of f than e of an. And it is the n plus first element of the sequence of better approximations. Repeat steps 1 through 3 until no improvements can be achieved. Braess has shown that there always exists a constant c greater than 0 if exponential sum e of an is not the best approximation. That is, step 3 of the algorithm can be successfully executed under this condition. Also, if the algorithm produces a sequence of functions converging to some exponential sum e, then e is the best approximation with respect to v sub n. However, convergence is not guaranteed. Back to the method of Braess. There is still the issue of what starting functions ei1 should look like, of how to start these sequences. The starting function for the calculation of the best approximation with respect to v sub 1 is the constant function e11. Note, here the best approximation is either an element of v sub 1 plus or v sub 1 minus. For the sets v sub n with n greater than 1, there are two cases. Case 1. The best approximation with respect to v sub n minus 1 is an element of v sub n minus 1 plus, and the error function has a positive alternate, or the best approximation with respect to v sub n minus 1 is an element of v sub n minus 1 minus, and the error function has a negative alternate. According to the theory, the best approximation with respect to v sub n is an element of v sub n plus or v sub n minus, respectively. In particular, this means that we do not have to worry about local minima, and start the calculations with this exponential sum. This is the most recent approximation plus this zero valued term where coefficient an is 0 and tn is different from all other coefficients ti. Numerical experiments demonstrate that the choice of Tn may have a bearing on the speed of convergence of the algorithm. Case 2 is a situation that the best approximation with respect to V sub n is neither an element of V sub n plus nor V sub n minus. We know from the theory that here local minima may exist and convergence of the algorithm is no longer guaranteed. As in case 1, we start the calculation with the most recent best approximation plus this zero value term where coefficient an is 0 and tn different from the other coefficients ti. If in the course of iteration sequences of two coefficients ti, tj converge to one common value, stop the iteration and try again with a different value for tn, which should be chosen such that the new sequence of exponential sums belongs to a different sign class. So in this situation, calculation of best approximation is an error and trial process. The theorems about sign classes, especially the construction and number of sign classes with better approximations, may prove helpful hereby. For function square root of x, best approximations have been computed according to the method of Braess. It took 3 to 5 iteration steps to calculate the best approximation with respect to V sub 1. For the calculation of the best approximation with respect to V sub 2, 0, for the coefficient t2 of the starting function, integer values between -15 and +14 were employed. 3 iteration steps were necessary with t2 between -12 and -7. 95 iteration steps were necessary for the starting function with t2 equal to +1. For the starting functions with t2 between +2 and +14, even after 99 iteration steps, the algorithm was not even near a best approximation. This demonstrates the sensitivity of the algorithm with respect to the choice of the coefficient tn of starting functions, and also that the speed of convergence may be extremely slow. For the calculation of the best approximation for 1 over 1 plus x with respect to V sub 3, 0, rather than following the method of Braess, two exponential sums e1 and e2 of V sub 3, 0 have been computed with the algorithm of Meinardus. With these starting functions, it took the algorithm of Braess 19 and 7 iteration steps respectively to arrive at the best approximation. What is surprising here is the fact that even though the norm of the error function e1 is significantly smaller than that of e2, and thus e1 might be considered closer to the best approximation than e2, almost as many as 3 times the iteration steps are needed starting with function e1. You find these calculations in detail in reference C2. This concludes the presentation of the algorithm and method of Braess. Next is an algorithm which builds on the method of Newton for finding the roots of vector-valued functions. Thus, for the purpose of this presentation, this algorithm is simply called Newton-X. The idea is to find the alternate points of the error function of the best approximation in analogy to the Braess algorithm. That is, suppose exponential sum e of a is not a best approximation and there exist two n+1 points xi such that the error function has alternating signs at these points. An example with n equal to 2. Error function e of x has these 5 extremal points at which the signs alternate. These are the extremal points of the error function. An exponential sum which has an alternate at these extremal points should be a better approximation. In any case, the value of its associated error function at these points is smaller than the norm of the error function e of x, which here is given at point x1. In general, starting with an exponential sum e of a0 with two n+1 points where the error function alternates, we look for a vector a1 with this property, which says that the error function of e of a1 has an alternate at these points. If the exponential sum e of a1 is a better but not the best approximation, find a new set x1 of two n+1 points at which the error function e1 has alternating signs, and find an exponential sum e of a2 with an alternate at these points. And we continue in this way. If the exponential sum e of a2 is a better but not the best approximation, calculate analogously a3 and then a4 and so on, until hopefully we arrive at a best approximation. This is an iterative process with these iteration steps. At each of these iteration steps we have to solve these equations. That is, at each step m we are given two n+1 points xmk with the properties from above and have to find a solution vector am for system 1 of two n+1 equations. This is where the Newton algorithm comes into the game. With these definitions of function gk and the vector valued function capital G with two n+1 unknowns b and q, a solution of system 1 is a zero of function capital G. To determine the zero of function capital G, the Newton algorithm is applied. This is the formal definition of the Newton iteration to be performed at step m. The iteration starts with this value, and this is the iteration formula, which is executed in practical computations in this form, where Jg is the Jacobian matrix of function g. Expansion yields this system of equations where dj denotes the jth partial derivative. If the linear space generated by the gradient of EBN has dimension 2n, this system has a unique solution vector S with these components Sj. And Bn+1 is the next approximation for the zero of function capital G. There is no need to calculate the exact zero of function capital G. It is sufficient for the exponential sum computed to have this property, which is the termination criterion for the Newton iteration. Now, putting everything together, this is the algorithm Newton-X. We start with an exponential sum for which two m+1 points xi exist with alternating values of the error function. Determine Zx of such points xi. An exponential sum with that property may be constructed, for instance, with one of the algorithms of video direct methods. In order to find a better approximation, with points at x execute the Newton iteration. These are actions 1, 2, and 3 until the error function alternates at these points, this condition. The result is an exponential sum e of Bn+1. If such an exponential sum can be computed, it becomes the exponential sum e of ai. Check whether e of ai is a better approximation than the previous one. If it is not a better approximation, the algorithm terminates with failure. If it is the best approximation, then we are done. Otherwise, that is, if it is not the best approximation, find a new point set x with this property and repeat step find better approximation with ai as starting vector b1. Obviously, step initialization may fail. We may be unable to find an exponential sum and/or a set x. Step find better approximations may fail too. The system of linear equations to be solved for the Newton iteration may not be solvable. A solution exists if the exponential sum encountered in the course of the Newton iteration are sufficiently close to the best approximation. And of course, as for the method of Braess, for Newton-X2, convergence is not guaranteed. Nevertheless, as this table shows, Newton-X turned out quite efficient in calculating best approximations for the Riemann-Zeta function. The starting functions for these experiments have been calculated with the algorithm of Meinardus. You find these calculations in detail in reference T1. This concludes the presentation of algorithm Newton-X. Next is a special case algorithm in that it calculates best approximations only with respect to V1. For the purpose of this presentation, this algorithm is called FJP-X. To the best of my knowledge, it was never published, but you can find it in reference T2. The idea is to find the alternate points of the error function of the best approximation in analogy to the Riemann algorithm. From the theory, we know that the error function of a best approximation a times e to the t times x has an alternate of length 3, that is, there are 3 points xi for which equations 2 hold. So, in order to find the alternate points of the best approximation, we could try to start with 3 points of the interval and calculate a first version a1 and t1 of the coefficients such that equation 2 holds. Most likely, a1 and t1 will give us not the best approximation, that is, its error function will not have an alternate. Therefore, we determine a new set of points, x1. They should be local minima of this error function, and of course the signs of the values of the error function at these points are alternating. For these points, new coefficients a2 and t2 are calculated, which satisfy equations 2. If a2 and t2 are not the coefficients of the best approximation, we keep calculating new coefficients a and t in this way until, hopefully, we arrive at the best approximation. This is an iterative process with these iteration steps. An example to illustrate this approach. To start iteration, these equidistant points have been chosen as set x0. With these points, equations 2 give us these coefficients a1 and t1, and this is the associated error function e1. R1 is the absolute value of the error function at these points. To calculate a better approximation, the extrema of error function e1 are selected. x12 instead of x02, x11 and x13 are the same as before. They are the elements of set x1. With these points, equations 2 give us these coefficients a2, t2, and this is the associated error function e2. R2 is the absolute value of the error function at x11, x12 and x13. This is a better approximation. In fact, here we happen to have arrived at the best approximation already. E2 has an alternate of length 3. At each of the iteration steps pointed out above, we have to solve these equations. Given 3 points xi, with the properties from above, we have to find the unknowns a, t, and r of system 3. Elementary operations give us these 3 equations. With this definition of function capital F, which is a generalization of this term here, and constant w, coefficient t is a zero of function capital F of s minus w. Since, by definition, this here is this equation. We get coefficient a from this equation with coefficient t plugged in. Now, putting everything together, this is algorithm FJP-X. For the calculation of a first approximation, select any 3 points of interval I, for instance, equidistant points as in the example above. Compute W1 and determine the zero of function capital F1 minus W1. This then is coefficient T1. If there is no zero, try another set of points. The algorithm may fail here. With T1 given, compute coefficient A1. If the error function is not equal to 0 for all points x1i, proceed with iteration step find better approximation. Otherwise, try another set of points and repeat step initialization. For the calculation of a better approximation, find points x and I such that the signs of the error function at these points are alternating and they are local extrema. Compute constant Wn, determine 0 of function capital Fn minus Wn. If there's a 0, this then is the coefficient Tn. Otherwise, the algorithm fails. With Tn given, compute An and proceed to step check for best approximation. If the resulting approximation is not a better approximation, the algorithm fails. If it is the best approximation, we are done. Otherwise, repeat and perform step find better approximation with the approximation just computed. As already noted, initialization may fail. A 0 of function capital F1 minus W1 may not exist. But the functions capital Fn minus Wn have a 0, and this then is even a unique one if function f satisfies these two conditions. And again, for FJP-X too, convergence is not guaranteed. Nevertheless, as this table shows, FJP-X turned out quite efficient in calculating approximations for the square root of x and the Riemann-Zeta function. You find these calculations in detail in reference T2. This concludes the presentation of algorithm FJP-X, and with the references which are available in the web at this address, we have also reached the end of this video. Thank you for your interest and goodbye. If the error function is equal to 0 at one of the points x1i, try another set of points